Thank you all for joining. Today we have Kristina Monakhova joining us to give the final TSC talk, I believe, of the fall. She's a researcher in computational imaging at MIT currently. She did her PhD at UC Berkeley, where she was affiliated with the Berkeley AI Research Lab and was supported by an NSF graduate research fellowship. She's currently a postdoc at MIT, supported by an MIT Excellence in Engineering Fellowship, is that right? And will be joining Cornell next fall as an assistant professor. So I think we're very excited to see what you've been working on, and thank you for joining us in person today.
Thanks for having me. Happy to be here. I'll tell you today about some of my work on robust and physics-informed machine learning for low-light imaging. And to set the stage, as you know, there are lots and lots of cameras around the world today. They do everything from powering all of the selfies that we take, to enabling robots to see, astronomers to study the furthest depths of space, biologists to study the very smallest cells, and doctors to make medical diagnostics. So, billions of photos are taken every single day, creating massive economic impacts and affecting people all over the world. And in my work, I focus on trying to make cameras and microscopes and telescopes more capable through the co-design of optics and algorithms. So by having this extra degree of freedom of designing optics and algorithms, we can have cameras that are more capable. They can do more than just take 2D images. They can maybe take 3D images, try to capture fast motion, polarization, phase, multiple wavelengths of light. And then we can optimize cameras on many other metrics. We try to make them as small and compact and cheap as possible. And in this talk, I'll focus on trying to make cameras see in the extreme low light and very photon-starved regimes. This talk will have 2 parts. The first part is going to focus on photography and trying to make cameras see in the extreme dark through physics-informed machine learning for the noise model. In the second part of the talk, I'll focus on a very different application of microscopy and trying to have our microscopes see in extremely photon-starved regimes, but then also say, how do we make our algorithms trustworthy enough for critical scientific applications? And how do we use that and kind of in the loop to make adaptive microscopy possible? So let's dive right in to the very first project, which is low light denoising. So the premise of this is that the best CMOS cameras on the market today need at least moonlight illumination to capture motion at night. So if the moon is out, there is enough light in the scene, you can capture videos with motion. And there's actually a show on Netflix that did this and had amazing videos of animal behavior on some of the darkest nights, as long as the moon was out. But if the moon is not out, there's so few photons that you need a much longer exposure time, and that precludes the capture of motion. So cameras can easily capture motion in daylight all the way through moonlight illumination. And in one of my projects, we tried to push this and demonstrated that we can see videos of extensive motion in starlight, which is submillilux levels of illumination for the first time. And the general strategy here is we want to have a camera that can see in the extreme dark, and you can't do that with your smartphone. So first you want to have a really, really good starting point. So we bought a very, very nice camera, and then we're going to try to push this camera to its limits, set it at the very highest gain settings, and then from there, we're going to need some sort of algorithms to denoise these extremely noisy videos. Now, the first building block here is a really good camera. So what's the best camera for nighttime videography? Well, you want to capture as much light as possible. So you need huge pixels to capture more light, a very large aperture on your lens to also capture more light. And it turns out that under starlight, there's not very much light in the visible range. There's a lot more light in the infrared. So ideally, we'd have a camera with near infrared sensitivity to try to kind of capture as much light as possible. And luckily, there exists a camera on the market that satisfies all of these things, which is this Canon camera, and it has this pretty interesting modified Bayer pattern where it has actually an IR channel. And so every single pixel in this Bayer pattern actually has IR sensitivity to try to capture as much light while still being able to take color images. Okay, so we got this amazing camera. Now the question is, do we even need any sort of clever algorithms? Can we just use this camera and see in the extreme dark? Well, to answer this question, we want to go somewhere where we can take interesting, compelling videos under submillilux levels of illumination, so under starlight. And if you take a look around at night in Boston, it's pretty bright, right? Like you can see a lot. I think even your smartphone camera can probably do a pretty good job here. And that's because if you take a look at kind of a map of how much light there is, we have a lot of light at night from street lights, from urban sky glow. And so, in practice, you can't get anywhere close to starlight levels of illumination around the Boston area. Fortunately for me, I did this project whenever I was in Berkeley, and there I could drive a couple hours north along the coast, and actually there's a lot less light pollution at night if you go far enough away from the city. And I went somewhere that was very, very dark in a place called Point Arena, California. And so we went there on a moonless, clear night, and we had a light sensor that measured how much light there was in the scene. And it measured there was indeed between 0.6 and 0.7 millilux of light present. So we had no external lights. And I took a bunch of videos with this camera at 5 to 10 frames per second. Now, just as a reference, I had my nice DSLR camera with me on that night, and I took a 30-second exposure, and you can't see much, right? So this is a 30-second exposure. You can see maybe the Milky Way, maybe the outline of some trees. Now we want to take this other camera and try to see motion. We want to see people dancing, people playing volleyball in this extremely dark environment. So with no algorithms, how well can our really nice Canon camera do? Well, here's what it can do. If we set this to the highest gain possible, here's a raw video clip at 10 frames per second. Now you can see something. I saw this raw data and I was very encouraged. I was like, okay, I can see that there's motion, there's a person there, and we can see a little bit of the background. If we contrast stretch this, you can see a little bit more details, but you notice that this video is corrupted by a lot of noise. And the noise is very structured. We see a lot of these sort of line artifacts throughout this. And so now, from this, we want to try to use some algorithms to denoise these video clips and get sort of compelling videos with extensive motion in this extremely dark setting. But what's the best sort of denoiser for these extremely high gain, low light videos? And denoising's been around for a very, did you have a question?
Yeah, so I just want to know where does the noise comes from?
So we're setting the camera to the highest gain, so there's actually a lot of sensor noise. So imagine if you have like a DSLR camera and you set the ISO up all the way. You're going to see a lot of these sort of artifacts where you actually have kind of like random offsets added to every row. And then we also have photon noise because it's very low light. So there's numerous different sources of noise here.
While you're interested in questions, how much light is lost to the bigger mask?
I mean, so there you definitely could do a little bit better if you didn't have color here. So if you just had a monochromatic scene. The goal here is to try to recover some semblance of color. If you notice here, the color is mostly gone anyways. But originally the goal was to try to recover compelling color, which we didn't quite achieve here. So I do think that you can get a lot more light if you didn't have the Bayer pattern.
Or you could have some kind of coded mask with various spectrum.
Of course, if you could custom design your own sensor for low light imaging, you can do a lot better. But this is kind of what we could do from an off-the-shelf camera. And so denoising has been around for a very long time. So can we just take some off-the-shelf denoiser and apply it to these videos, and then maybe the project is finished, we're done, right? Unfortunately, most denoisers that you find off the shelf assume kind of additive white Gaussian noise. And a lot of times they're designed to work in kind of bright daylight settings. So if we take a look at some of the kind of the best classic denoisers, which is VBM 4D, and apply it to our videos, you still get a lot of these blind artifacts throughout this, and the video is not very compelling. The same is true for an off-the-shelf deep denoiser. It's optimized for, you know, Gaussian noise and bright daylight scenes, so obviously it does not work for our extremely dark setting here. So okay, off-the-shelf denoisers don't work. Instead of doing this, can we collect a real data set of noisy and noiseless images? This is actually not so difficult to do. We can do a high gain short exposure image and then the corresponding low gain long exposure noiseless image, and then train a denoiser from scratch, where it'll aim to denoises compared to the real image and hopefully get back a nice frame by frame denoiser. However, this has one big problem, and which is that here you actually, like, you're not using all the information. If you do a frame by frame denoising, there's a lot of information across frames that doesn't change or that moves a little bit. And if you just denoise a single frame at a time, you lose all of that. And in practice, you get a denoiser that has a lot of flickering and still has a lot of artifacts and not so much detail in here. And so if you train just a single image denoiser and apply it to these sorts of videos, it doesn't do so well. So okay, naturally, rather than taking a data set of images, can we instead take a data set of videos and then train a video denoiser that leverages multiple frames at the same time? Well, this has one big experimental limitation, which is that this is experimentally very challenging to do, because if you have these short exposure, long exposure videos, how are they going to be motion aligned? So experimentally, it's really tricky to collect this sort of aligned data set of noisy and noiseless images. So we said, okay, none of the off-the-shelf denoisers work. We can't create our own data set. This problem is impossible, right? Okay, well, there's one other thing we can try, which is to say, okay, maybe we can't use any real data from our camera, but what if we had a really good noise model for our camera? So we can go from a noiseless video, which we can take off the shelf. There's a bunch of videos online we can use. And then we can kind of generate synthetic noisy clips that look very similar to the images from our real camera. Then we can actually train a video denoiser using synthetic data and see whether that will work on real measurements from our camera. But the problem is, what is the best noise model for this sort of extremely high gain, low light setting for our camera? And if we take a look at just a Gaussian noise model compared to real data from our camera, it looks very different. It's a little bit hard to see on this projector, but the real noise has a bunch of these line artifacts, and the Gaussian noise doesn't quite match that. So there exists some really good off-the-shelf low light noise models where you can take some amount of data from your camera and try to calibrate a few parameters and try to have it match the real noise you see on your camera. And we've tried this out. It does a little bit better. However, it's still a little bit off. It doesn't quite match the real noise in our camera. So we said, okay, well, can we try to, we can easily collect a data set where we have some noisy bursts, a corresponding noiseless frame, no motion. So can we use that to do the opposite of denoising? Can we say, let's learn the best noise model to go from a clean image to a synthetic noisy image? We can then compare that to the real noisy image from our camera. The problem with this is that if you do a pixel-wise loss between these, so if you compare the synthetic and the real noise, each pixel is going to be different every time because the noise is stochastic. So something like mean squared error might give you a very different answer every time. So instead we said, okay, rather than comparing this pixel-wise, we're going to have a second network, the discriminator, which is going to compare the entire distribution of the noise and say, okay, is this real noise or synthetic noise? So we ended up training a GAN to do this, where you have a noise generator, which is going to try to, create very realistic synthetic noise. And then the discriminator is going to try to say, okay, is this real or is this fake? And whenever these are trained together, hopefully in the end, we'll get some compelling realistic noise. However, GANs are notoriously hard to train, and we want this to generalize and work on real data from our system. So we decided to constrain the GAN a whole bunch using some sort of physics-based noise parameters. So if you take a look at a textbook for what sorts of noise you might see on a CMOS sensor at extremely high gain, there's a few common things that you see. For example, one thing is there's row noise, where we have a random added offset to each column. And that's something that we can parameterize as this Gaussian with an unknown standard deviation. And that's one parameter that we can actually have our GAN learn. It's just the standard deviation of this row noise, for example. So you can parameterize this and have just a few parameters that describe the noise, which our GAN is going to try to learn from the data. So rather than having to kind of hand calibrate the noise model, we have this data-tuned noise model, which the GAN is going to basically like learn the right parameters for the noise. And then for anything that we don't account for in this noise model, we're going to have a small CNN, which will compensate for any model mismatch. So, okay, after training, if we compare our model to Gaussian noise on the right, then the best low light models, and then here's ours. So ours matches the real noisy data a whole bunch better, and it is able to capture kind of all of these sort of like row artifacts, and is able to realistically synthesize noise from our camera at this single high gain setting. So, okay, now we have a noise model, and we want to take this and actually use it for denoising. So with this noise model, we can use a bunch of data sets from online, because for video denoisers, you need a lot more data than for a single image denoiser. So we use a lot of data from just RGB videos from online, which we pass through our noise model to generate synthetic clips. And then we also use some real noiseless videos from our own camera, because we have this modified Bayer pattern. So we don't actually have RGB, we have this RGB plus IR. And then we use some real still clips from our camera as well. So, okay, so we use all the data we can possibly find to train this video denoiser, and let's see how well it does on real data from our camera. First, I'm going to show you some still images so we can compare this and actually have some ground truth. So here's a raw, noisy still image from our camera. Then using one of the best classic denoisers, it doesn't do so well. There's still a lot of these line artifacts. The same is true for the best deep denoisers. And then a single image method retrained with our own data, it does quite a bit better, but it's missing a lot of the details. And our method, which uses multiple frames, is able to preserve a lot of the fine features, like the text in this book, compared to here, and it more closely matches the ground truth. But the real test is how well this does on the videos in submillilux, in the extreme dark. So let's see how well this does. So here's a raw clip taken in the extreme dark, where it's so dark that I couldn't even see my hand in front of my face. And let's see how well our camera can see. So if we contrast stretch the video, you can see some more of the details. Here's the best classic method, one of the best single image deep methods, off-the-shelf deep method, and then here is ours. So it's a little bit hard to see here, but we're able to actually maintain a lot of the fine details. You can see the flags waving in the wind. And if I go to the next slide here, we can actually pick out a satellite moving across the night sky. And once the video replays, you can actually see a shooting star across the sky. So it's going to play very soon. And there it is. So we're able to have such high frame rates. This is at 10 frames per second. That we can actually, see satellites, we can see shooting stars, we can see flags waving in the wind, and we can still see actually a bunch of detail on this cactus here. And this is taking in submillilux with only the light of the stars to illuminate the scene. So here's a few more examples. Here's a raw noisy clip, and then here are some of our process results where we're actually able to, see people dancing by the light of only the stars, playing volleyball and spinning around. The background there is actually the Milky Way. So the bright part of the sky is actually the Milky Way, which normally with my own camera takes a 30-second exposure to see, but we're seeing the Milky Way and all these details at 10 frames per second. So I thought this was really exciting. So that concludes this project. We basically were able to show photorealistic videography in submillilux for the very first time, pushing the limits of what cameras can see by order of magnitude. And we have an open source data set of submillilux videos with lots of motion. And we show that you can kind of, you can try to kind of push the limits of cameras by saying, okay, if you can't easily model what a camera is doing because it's nonlinear, for example, perhaps you can do that with some sort of neural network, which can kind of approximate the camera's behavior at something like an extremely high gain, low light setting. Yes.
I imagine this is very specific to that particular camera.
Exactly, yes.
If you need to transfer to a different model of it, a different unit, do you have to retrain the whole network, or can you retain some of the learned parameters?
So in practice, whenever you push a camera to the limits, oftentimes you have very camera specific sort of behavior noise. And so if you were to have a different camera, it's going to behave a little bit differently. So if you wanted to work as good as possible, you would need to kind of retrain it. The thing is, though, if we go back a few slides, the training is not the way you actually collect the data set isn't so hard, because all you have to do is set your camera up and say, okay, I'm going to trigger it to take 100 noisy images for every 1 or 2 noiseless images with longer exposure, and do this for a grayscale target, maybe a few other targets. And then after, a couple minutes, you're done. So this is something that I imagine in the future, it could be done in the factory. You could have some sort of data-driven calibration, and then they could perhaps model any sort of nonlinear effects that are camera specific. One of the big limitations with this is that we trained it only to work for a single ISO, essentially. So only the highest gain, because that's the case we're the most interested in. So there's a lot of potential in having kind of more general models that work for any sort of camera settings.
So a question just came through online, maybe a follow-up to Josh's, and feel free, Tim, I'll read it, but if you want to chime in. It says, is it specific not only to the camera, but also to specific camera settings, like exposure?
Yes, so it is specific to exposure and the gain setting.
I have a question. So quite interesting. So the data set you took from the public one didn't have the IR, and yours did. How did you kind of reconcile that to use both of them constructively?
Yeah, surprisingly, we didn't do much. So there's one of the big problems is also the fact that the online videos are all JPEG, and we're processing everything in RAW. So there is some existing methods that will kind of unprocess the JPEG and give you something that's a little bit more like a raw image. So we did that, but in terms of going from RGB to RGB plus IR, we did nothing. We said, okay, we're going to pre-train the network with these RGB images and then fine-tune with some of our own images that actually have the IR, and that worked well enough in practice.
Thank you.
So one more question that came through on the chat. It said, for the video data set collection, instead of collecting paired data under starlight using longer exposure, would it be possible to collect the data under moonlight and then simulate the starlight condition using like a low light filter on the
I think
lens?
that's a great question, and that's something that we didn't look into, but one of the problems that you find is that, if I go back to one of my first slides, you have kind of a change in the distribution of the light that's present under moonlight and starlight. So you might see some very different sort of behavior and performance. That's not to say it wouldn't work. So I do think you could take a bunch of images under moonlight, but you still have this problem. You cannot take paired video data sets. So you can certainly take some still images under moonlight. And actually, for the real data that we used, we did exactly that. We take a couple of images under moonlight, and we also took a bunch of images under daylight to capture this this noiseless data set from our camera. And that ended up working well enough, and actually transferring it ended up working under starlight, even though a lot of the images that it saw were with RGB and moonlight and also daylight. So yeah.
So looking at that response curve, it's clear that you really only had red light coming in. So that, and that's why there's basically monochromatic results. But it's well known that certain parts of the IR band are highly correlated with parts of the visible band, particularly on vegetation.
Mm-hmm.
So I was wondering if you had enough data to pick that up, or if you had the network model that could have exploited it, had there been enough data.
Yeah, that's a great question. That's something that we didn't explore, but something that's really interesting, potential future work. I do think that in some of the videos we're able to kind of get a sense of some of the color. I guess maybe you don't see it so much here, but sometimes you can kind of, the shirt, the bear there is yellow, and you're able to kind of see that in a few of the frames. And so it does a little bit, but I think there's a lot more that could be done here in trying to try to colorize this. The question is always like, is there enough data to actually know the real color, or are we just going to be guessing it? And I think it's actually okay to guess it, because we like to have kind of like natural, interesting color images that we look at. So if it's not for some kind of scientific application, I think it's fine just to take this and try to recolor it. But I do think there is some information that maybe you could get something that's a little bit more reliable and actually try to infer the true color.
There was a hand. Yeah, Hassan, I think, raised his hand.
Yes, hi. I had a question about the physics-informed portion of this. Is that primarily in how you incorporated the, let's say, the preliminary portions of the noise model? Are you able to go back to that slide?
Yes. Yeah, exactly. So I'm calling this physics-informed because we kind of know the kinds of noise that's generally present in CMOS sensors at extremely low light, high gain settings. And so if we know what sorts of things we expect to see, if we don't know the exact parameter of it, we can model that and then try to kind of like learn these sorts of parameters from the data.
I see. So the parameters over here that you're learning are primarily the lambdas that we're looking at, potentially probably weights to define how these additive noise terms are being combined together. And then finally the CNN to kind of refine the whole process. Is that correct?
Yes, exactly. So like the lambda, so we're learning the kind of the standard deviation of some of these parameters or some of these distributions.
Right. Okay, thank you.
All right, so now I'd like to switch gears and talk about another application where rather than doing this for photography, we want to focus on microscopy, where a lot of times you're extremely photon starved, and see how we can not only denoise these sorts of low light images, but also give some sort of guarantee to scientists and biologists that what our algorithm is predicting is really there. Because you really don't want your algorithm to hallucinate information for biology, for science, for medicine. Okay, so the premise is we want to do this for multiphoton microscopy, which is a very popular imaging method for the non-invasive imaging of thick or living samples. And it's based on this nonlinear interaction of ultra-fast laser pulses and biological tissue. So multiphoton microscopy is really, really popular. It's been used to study neuroscience, cancer, and many more things. The key takeaway is that it's a scanning system. So basically, you have a sample, and then you have a pulsed laser that's going to scan the sample pixel by pixel to make this image. And so, because it's a scanning system, we have a trade-off here, because you don't take an image, you just acquire a single sample at a time. And so if you have a laser that's set to a higher power, and you stay at each point in your sample for a longer amount of time, you can get a really compelling, amazing image that's practically noiseless. But every time you shoot a high power laser at your sample, you're damaging your sample. So maybe you can only scan it once, and you can't scan it over and over again to see dynamic samples. Then if you have some sort of motion in your sample, if it takes a very long time, it takes you a whole minute to scan it, you're going to miss all that motion. So there's this trade-off because it's a scanning system. So you could have something that's, much lower power and has a shorter dwell time, so you stay at each point for a smaller amount of time, but you have much worse image quality. Your images are very noisy. However, it comes at the benefit of you have a lot less sample damage. You can scan really fast. You can see motion. You have a much larger field of view. And so biologists, they want to see, bigger. They want to see deeper. They want to see dynamic things. And this is something that the current microscopes can't do, because you get these extremely noisy sorts of images. So we said, okay, well, let's frame this as a denoising problem. If we can collect these sorts of, really noisy images, but we can scan really fast with very large fields of view and with lots of motion, that's a win for everyone. And so we're going to kind of frame this as a denoising problem, say, okay, can we take a noisy measurement from our microscope, then denoise it? But then one of the big problems is, can we trust this denoised image enough for scientific and medical applications? And since this is a scanning microscope, you can take multiple images at a time. And the other question is, can we sample these in a better way? Like, if you know something about your sample, can you do this in a more clever way? Do you have to rescan the whole thing every single time? And I'll talk about both of these two problems throughout the second half of this talk.
Is there a difference in cost for scan direction, like X, Y, and Z?
So it depends on the system. So actually, a lot of times the system that we had, it's very easy to scan an entire line, but it's not so easy to skip points within that line. And so, you don't really have random access so much as you just have like kind of a line scanning. And that's one of the big limitations that we don't address that in this work. There are other people who have, much fancier microscopes that can do actual random access very easily. So it really depends on the hardware of the lab. Okay, so first let's address the first problem. And we're going to address this in terms of uncertainty quantification. So kind of like for each pixel in this denoised image, can we try to have some sort of notion of how much we trust it? And we're going to do that through uncertainty quantification, which will give us a sense of how much we trust each pixel. So there's a lot of methods for uncertainty quantification that have been around for some time. In the deep learning community, one of the most common techniques is based on Bayesian dropout. What that means is that you take your network and you randomly drop out some of the weights, and then you'll do multiple forward passes, and you get multiple different images. And if you do this, 100 or 1,000 times, you'll get some estimate of how much does the image change as you do this sort of dropout. But this is, very computationally expensive because you have to do, some large number of forward passes through your network. The other common technique are these ensemble techniques where rather than having one network with dropout, you actually just train some large number of networks. And then you say, okay, well, I think that they're going to somehow, during training, they're going to be a little bit different each time. And we'll have different images each time, which will also give us some sense of uncertainty. But the problem with both of these two methods are they're computationally intensive because you have, n forward passes or n networks. And this is kind of a heuristic. Do we really trust this to give us the true uncertainty of both the algorithm and the data? Some people say, yes, maybe, but is it enough for scientific applications? Well, recently there's been another method proposed for uncertainty quantification that's based on something called quantile regression and conformal risk control. The thing that's really great about this technique is it's really fast. You only need a single forward pass. You actually have rigorous statistical guarantees that some fraction of the true signal lies within the bounds that you predict, and it's distribution free, so you don't have to have any prior assumptions about the network or the data. I'll go through this in detail, but one thing that was really exciting about this work is they tried this on MRI, and they were actually able to pinpoint an area of hallucination. So here is in red is areas of high uncertainty. And I believe the right is the ground truth and the left is the prediction. And you see in the prediction, there's this kind of like extra feature here, which isn't present in the ground truth. And so their method is able to pinpoint this, saying, okay, this region has high uncertainty, and that corresponds to a region where the model hallucinated. So that's really encouraging. So how does this work, and how do we use this for microscopy? Well, we can formulate this as kind of a standard denoising supervised learning framework where you have some sort of training data, you have noisy and ground truth images, you want to train some network to denoise your data, and we're going to compare it with the ground truth. But now a standard supervised learning setup has a symmetric loss like mean squared error. What we're going to do instead is we're going to predict not just the image, but also the lower bound and the upper bound. So our network gives us, the image and then also a bound for each pixel in that image. And we're going to do this with an asymmetric loss. Now, what I mean by that is if you take a look at something like mean squared error and you plot the loss, so the prediction minus the ground truth, it's the same on either side. So if your prediction is too high or too low, it's going to give you the same loss and try to get everything to go towards the mean. Now, instead, we're going to use a quantile loss or a pinball loss, which is an asymmetric loss, where you have this tuning factor alpha, which will change how much it's skewed. So for example, whenever alpha is 0.5, it's symmetric. But if we change it to be 0.2, it's going to be skewed to this direction, which means that if our prediction is too high, we're going to have a larger loss value. So it's going to encourage the network to produce something that's smaller than the mean. And you can tune this to be even smaller, or you can flip it to the other direction and say, okay, if alpha is bigger than 0.5, we're going to penalize underestimates a lot more and encourage our network to produce something that's bigger than the mean. So in that way, we can basically say, okay, we can tune these alphas to give us a lower bound and an upper bound and encourage our network to produce these two images. So, okay, so far we have one modification to our network. We change the last layer to produce a lower bound and upper bound, and we have a new loss, which will penalize the prediction to produce a lower bound, the image prediction, and the upper bound. And this is really fast after training, but the question is, can we actually trust these bounds? How do we know that it's actually producing the correct bounds? So it's already very fast, but we don't necessarily trust it. There's no guarantee that some fraction of the true pixels actually lie within these bounds. So that's where conformal risk control comes in. And this is the second step. So after training your network to produce this confidence interval, you have a second step where you have a held out data set of calibration data where you say, okay, we just want to scale these bounds, make them bigger or smaller until they have some fraction of the true pixels within there. For example, if you want to say, okay, I want to have 90% coverage, so 90% of all the true pixels lie within these bounds, we'll just scale this bigger or smaller until that is true for the calibration data set. And then you actually have statistical guarantees that, if your calibration data set is similar to whatever you're actually using this for, then in expectation, these bounds will hold the true signal. So, okay, so this is the premise of the work.
This is a pixel by pixel scale.
So there's a single scalar here, which will the bounds give you a pixel by pixel interval. It'll just scale it. So everything's scaled the same way.
Scales all the pixels.
Yes, yes.
I mean, so there are many ways we could get this to expand to fit, like you could do a scale on a shift one. There are many ways to find 90%.
Right, and so kind of the idea here is that like the network is already giving you a good sort of bound, which is using information across the entire image to estimate how much we trust those pixels. And here we just want to kind of scale it a little bit bigger, a little bit smaller, so that it's a tighter bound. Right, but I'm saying there are actually many ways you could do that transform. What makes this the right one? So what makes this the right one is our collaborators in statistics at UC Berkeley, who told us that with this procedure, we have rigorous guarantees. This is a trust-like argument. So, I mean, I do think I'm sure there are failure cases, but if you have a big enough calibration data set and the data that you're using this on is similar in distribution to your calibration data set, they should be able to pinpoint hallucinations. And I think that, nothing is perfect, but this is much faster than previous methods. And it does give you some guarantees. So, okay, so now we have something that we basically, we'll run our noisy image through the network, scale it by lambda, and we have an upper bound and a lower bound. And then if you subtract the two, you have a pixel-wise uncertainty score for your image prediction. And, in practice, we want to do this not just for, a single image, but as you saw from the first part of the talk, it helps a lot if you can do this with multiple images where you use information across multiple frames to denoise and predict your measurement. So let's see how this works on real experimental data of human uterus tissue on the multiphoton microscope. So if we take a single noisy measurement, we can denoise it, and compared to the ground truth, a lot of the features are missing. And if we look at our uncertainty map, there's a lot of pixels that are very uncertain. Then if we use 3 measurements, you can see that the uncertainty goes down and we see more features. And for 5, you see even more features, and the uncertainty goes down even further. So let me scroll through these. You can see that as we use more noisy frames, the prediction gets better. We're able to see more of the true features within the ground truth, and our uncertainty goes down.
So I can believe the mathematical arguments, but what I'm seeing is that where you don't have information, dark areas is where you have the most uncertainty.
Absolutely. And so actually the first time I saw this was a few years ago. There was a different paper in microscopy doing the Bayesian dropout, and they showed the same thing. They showed, okay, uncertainty is high where there's signal. And I said, I don't believe that. Shouldn't uncertainty be low where there's nothing? But in practice, the regions that first of all, there's photon noise mostly here. So as your intensity is higher, there's going to be more variation. So that's one argument of saying, okay, so that actually matches. there it will be more uncertainty where there's more signal. And then, I mean, also like our network can see that there's not really anything there, right? And so we have a lot more confidence that there's not much there, but we know that there's something here, we don't know what it is. And so we're seeing that in the uncertainty of saying, okay, we know that there's something here, but we're not sure what exactly is there. And as we, scan and see more data, you can see that the uncertainty goes down in those regions, and we're more confident about certain areas in the measurement.
Okay, but the uncertainty map looks so much like the denoise image. How much information does it really carry beyond that Poisson argument about what X to Y pixel variance is?
So I think one of the well, okay, so if I go back to the previous
If we look at the
approach.
uncertainty map in grayscale, would it be significantly different than the denoise image?
So if we compare kind of like 5 images versus 1, you can see that the uncertainty is high everywhere, right? And it does correspond to where there's signal. But it's going down as we have more confidence within the estimate. So it does indeed, correlate with where the signal is. I imagine if we could take this kind of to infinity, have more than 5 measurements, we could have like 100 measurements. I would assume that this should go down all the way to 0 at some point. Unfortunately, we have some practical limitations here where our networks have a fixed number of inputs and outputs. So we couldn't just say, okay, let's train this for 1,000 images. It's kind of a challenging thing to do. So we said, okay, we're going to bound it at 5. And it's kind of showing the right trend. I think that it would be more compelling if we could do this to infinity.
It's an interesting prediction. I imagine at infinity, we always still have Poisson ones, so that in fact it would converge to the identical. Rather than to a 0 variance, you would converge.
But I mean, if you have a say 1,000 images of the same scene and you can average that together, that's kind of what the denoiser is doing at that point. It's just averaging everything together. And then the Poisson noise is also averaged out.
It shrinks, but it's always there.
Mm-hmm. So yeah, I think that would be a really interesting experiment to run.
The network is taking in the 5 measurements separately, like as
It's
separate inputs.
combining into, yeah. So one of the big problems with this approach is that a network doesn't have a flexible number of inputs and outputs. So we said, okay, let's do the best we can do, which is whenever it has 5 measurements, we put in all 5 measurements. Whenever it only has 1 measurement, we're going to repeat that 5 times. Which is similar to what they do with like transformers. They usually just kind of like 0 pad the end.
Have you considered like attention-based approaches or like neural field approaches for this kind of thing?
Yeah, I think that would be a really interesting future direction. Okay, so let's continue on. So now that we saw that, okay, the uncertainty is shrinking, and we have some sort of notion of how much we can trust the prediction within our images. But now the second part is to say, can we use this information to sample in a better way? And there's a lot of different methods in microscopy for adaptive acquisition, but usually you assume that maybe you have like a really good pre-scan, you can segment everything, and then you can just rescan those areas. And we say, okay, but can we sample in a way that's both algorithm and sample informed? And this naturally comes out of the previous few slides where we say, okay, we'll take 1 measurement, we'll denoise it, we'll get the image and the uncertainty, and then we'll threshold it and resample only the most uncertain regions within our image. And then as we go through this process, we're sampling fewer and fewer of the pixels within our image. And we're doing this without any sort of ground truth segmentation for this. So we're kind of, you can think of the uncertainty as kind of almost segmenting your image, but also doing this in a way that, you know, as it's more certain about certain regions, the uncertainty goes down, so we don't rescan those anymore. Okay, and so if we do this, we can basically get this sort of adaptive acquisition scheme, where you can denoise the image compared to the ground truth. And doing this sort of adaptive scheme, you can do something that's about 120 times faster and with less light dose than the ground truth. And of course, it's not perfect. The uncertainty is still, there is still like quite a bit of uncertainty in these images. But at least we know which regions we can trust more than others. And I think this is really interesting for biology because one of the big things is we want to sample as fast as possible with as little light as possible, because we want to go deep into tissues and see things that are moving. And this is something you can't do if you just collect this nice ground truth image. It takes way too long. So here we're able to do something that's quite a bit faster, and still has some sense of uncertainty. I do think ideally it'd be nice if the uncertainty went down all the way. And I think it's in future we're going to try to see how far we can push that. And as you saw before, if you have just a single image versus 5 images, you're able to see more features, which makes a lot of sense. Which is why I think this sort of adaptive acquisition is really promising, because you can kind of resample the uncertain regions within your image. Okay, so with that, let me conclude. And
Oh yeah, we had a hand online.
okay, yeah.
Go ahead, Hassan.
Thanks, Gordon. I'm just curious about what the let's say the uncertainty module is actually picking up on in terms of features in the denoised image. To some extent, it looks like blurry regions in the image are generally considered to be uncertain. First of all, is that a correct observation?
Yeah, it does seem that that's true. Because you can see here that all of this is very uncertain, and as we increase the measurements, uncertainty does go down, and we have more features going through, which makes a lot of sense because if you have a single noisy measurement that looks like this, you shouldn't be able to hallucinate fine structures in your sample. You want to get something that does the best that it can with the data that it has. And if you have more and more images that you can try to use together in a denoiser, you're going to be able to see finer structures and features than your sample.
Right. So in a sense, you're basically training what I would consider to be something similar to a discriminator that is assessing the quality of this reconstructed image at the pixel level. Probably it's using local information to determine whether or not that region appears to be a realistic output versus something that has artifacts that are caused by the network.
I think one of the problems with having a discriminator is that if you have a discriminator that does this, and your network produces something that's realistic but totally fake, the discriminator wouldn't know, right? So I mean, like, if you have a really good denoiser, if you use a diffusion model, for example, it's going to hallucinate you a beautiful image. And how will the discriminator ever know whether it's real or not? So I think the uncertainty is doing something a little bit different, a little bit more powerful, which is trying to assess itself and say, how confident am I in my prediction?
Okay, I'm actually glad that you mentioned the diffusion example. So if you were to actually synthesize, if you were to train a diffusion model that would synthesize something that would look realistic, will your uncertainty module actually be able to detect that there's uncertainty?
So there's actually a really interesting paper that came out a little while ago that's called confusion. Because the method I'm talking about here uses conformal prediction. And so it actually uses the same exact method for diffusion models. And it says, okay, whenever we want to do something generative, can we have a lower bound, upper bound for the images that we produce? And they have some really cool results showing, okay, if you have kind of this average face, then what is the range there? Like, you can have something that looks very different. And so they have a couple of examples of doing this in a generative setting while still kind of quantifying this sort of uncertainty. So
Okay.
check it out. I think it's a pretty cool paper.
All right, thank you.
Okay, so that concludes my talk. I'd like to acknowledge the Waller Lab at UC Berkeley, my collaborators at Intel for the first project, and the Yale Lab at MIT. And I'd like to make a quick pitch. I'm starting a brand new lab at Cornell. I'm looking for, if you have any talented students you'd like to send my way, or if you'd like to collaborate, or if you want to give me some money, let me know. I'm happy to take any more questions.
I think we have one more online. Tim.
Yeah, hi, that was a really great talk. Thank you. I'm wondering if you checked with I don't know, with test data, how good that 90% uncertainty prediction really is. I know you tuned it on validation data, but I wonder in practice how well it does the uncertainty.
So I mean, the thing is, if you have real data, the question is, do you have your ground truth? And so whenever we did this, the 90% confidence interval, we scale it so that if you say you train with like some amount of data, then you have some held out calibration data you can scale these sets on, then you have a guarantee that yes, it does contain 90%. And if any new images are similar to those you see in your calibration data set, it should still hold and you should still have 90% of the true signal within those regions. Does it work for all samples? If I say I'm imaging and I change my system, I have a different power for my microscope, or if I have like a longer or shorter dwell time, no, it's not going to work. So it's very specific to kind of how you train the network and your calibration data set. So as long as everything is the same distribution across this, then yes, it should still have some guarantee that some fraction of the true signal is there. And by the way, the 90% you can tune, so you can have it be 99% if you want. It'll just make the interval a little bit bigger.
Are you scaling in the log domain? Or, I mean, you have a problem with this floor, right? So if your average is fairly low, but you have some samples that are high value, you can't just scale your boundaries without also including negative values in order to get the higher.
Yeah, so I think an interesting open question is, is this the best way to do this? Can you try to scale these intervals in a better way than just having some sort of constant scalar? And I'm sure that there's a lot of potential there in saying, okay, maybe you want to do this in log space, or maybe you want to do this in some sort of feature space instead. So I think there's a lot of open questions. This technique that I presented is pretty new. I think it's been used for just a few years. So I think there's still a lot of space to apply it to interesting problems and see how we can optimize it for those applications.
And more generally, I mean, you have a value of information for which normally the appropriate model is some kind of reinforcement. Right? You want to have a policy for scanning, basically, an optimal policy that whatever gets you the most certainty for the least energy expended in sensing. That's to take into account the foibles of your particular machine. Couldn't you just wrap your whole predictor in an RLE setting and just learn a policy for scanning?
Probably. One of the issues there is, so you would need to do this in simulation. So if you had a very good simulator for your system, then yes. If you don't have a very good simulator for your system, then no. I think one of the problems is also that, we want to do this for kind of like thick 3D samples, and the data sets for that, for multiphoton, I don't think they really exist. So you want to have something that can, synthesize these on the fly, and it'd be really cool if we could do that.
Your predictor is essentially a simulator for the purpose of training do learning algorithms or something like that.
Yeah, I guess I just mean that we just have some small data set of real data from our system, and if you were to have a simulator that was perfect for your system, you could do this in the loop, you can have many different policies, and it'd be a little bit more powerful.
What do biologists consider to be the frame rate that they need to?
Oh, so it varies a lot. I was talking to a physicist at Cornell recently, and he was telling me that, he's invested everything that he can in his optics. His microscope is optimized as much as it possibly can be. And there's just not enough signal. He cannot image these these large living cells. The field of view of the microscope is really, it could be much larger and they can go that far, but they don't have enough signal. So they have to scan a much smaller area. They can't do 3D, they can't do moving targets. So I think there's kind of like, we reached the end of how much we can optimize our optics, and we really need to start thinking about co-design, saying, okay, can our algorithms help us? Can we sample in a better way? Can we trust some denoisers to do some of the work for us? So I think really that's kind of the limit. Like if we can do this, then we could, push it much further for biology.
And actually, as far as the scanning diagram, I assume that's kind of cartoonish. Would you capture the light that's scattered in all directions rather than the light that's coming back through the lens?
Could you capture all? I mean, it depends on the lens that you, right? So you can have like a very high NA lens and capture everything. I'm not sure if you'd want to, because you might have some light that's scattered like the wrong from other things there. So multiphoton itself actually, like, let me go back to that slide. So it has like a very small point spread function, because you have to have 2 or 3 photons of light interacting within your sample for it to work. So the signal is actually very weak, but it's very sharp already.
And the photon, this is because the fluorescence requires a cascade of energy.
Yeah, so oftentimes you don't just have like a single photon that has to interact with the particle. You have to have multiple ones. And there's also other things like second harmonic generation, third harmonic generation. We have to kind of have something like happen within there, and you have to have a very high power pulse laser for this to actually even work in the first place. And so in practice, your PSF is very compact.
Is it sort of depth specific too? Like, very high XY resolution. Are you also targeting a particular depth plane for these things? Yeah, so multiphoton can see deeper in general than single photon. And if you do like 3 photon, it can do much better than 2 photon. In practice, the point spread function is not the same in Z, so you actually have a little bit better XY resolution. Maybe related to that, the noisy images have this like patchy look to the, is that just yeah, like almost block artifacts? Is that particular to the scanning system, or? Yeah, I'm not sure. So in an ideal setting, you would only have Poisson noise. Yeah. This is a home-built multiphoton microscope from a first-year PhD student. So there might be other things going on. So we actually noticed that if you have a really bright signal, sometimes the next point you scan will be a little bit oversaturated. So there is a little bit of kind of like a dependence on the scanning. If you have the perfect multiphoton microscope, you wouldn't see that. But in practice, it's really hard to have the perfect microscope. So you might have some kind of hardware-specific noise here.
I think Hassan has his hand up on Zoom.
Yeah, sorry, I had one more question actually back about the first part of your talk. And this is related to basically you've invested a lot in trying to learn a noise model so that you can actually generate noisy images. And then you're training effectively an end-to-end network that's learning to denoise that. Your reconstruction process, wouldn't that benefit if you were to invert the process of actually generating the noisy samples? either through a map estimator, like, or some basically unrolled or unfolded map estimator. Do you think there would be any gain in that?
Yeah, I think that's a really interesting question. And I think there's a lot of potential in trying to like leverage the noise model that you already learned within the reconstruction. It's just not immediately clear exactly how to do that. I think there is maybe some strategies going forwards. But yeah, I think it's an open question, and I definitely think it could help.
Thanks again.
So is there anything about any particular algorithm or signal processing strategy that would make you want to change the acquisition process of the optics?
So in some of my other projects, which I don't have up here, we did exactly that of saying, okay, we want to use a 2D sensor to capture 3D or hyperspectral. And there we say, okay, well, we kind of know what algorithm we want to use, and now we want to kind of design the optics around that. And you can do that for compressive imaging. So in one project, we did this for hyperspectral imaging, where we kind of designed the optics such that it's optimized to recover hyperspectral volumes from a single 2D sensor. And I think there's a lot of potential in end-to-end design where we say, okay, well, maybe we could have a differentiable optical model, differentiable sensor model, and some algorithms, and we want to try to kind of co-design these. And there's been a lot of work in this field recently, and they've shown a lot of promise.